Is that okay?
Yeah. Good.
Okay. So I think it's okay if you ask questions during the seminar in case something is not clear. Maybe, Shulei, if you can tell me if there is a question, because I may not see all the people raising a hand or the virtual hand. So I will talk about charge spin conversion effects. These are essentially effects where an electric current is converted into a spin current, and then show how this spin current can be used to do something useful, at least for us, which is control the magnetization of thin films or nanomagnets, and also sense the magnetization. And all of this is due to spin-orbit coupling. Now, before starting, I'd like also to acknowledge the contribution of the students that contributed to this work, the students and postdoc, Eva Grimaldi, Viola Krizakova, Jan Avci, Christoph Moore, Christian Stam, and others. And also a collaboration with IMEC. IMEC is a R&D center in Belgium where they essentially develop electronic applications. They are a bit of a bridge between academia and industry and work based on industrial contracts. So spin-orbit coupling, I think we all know what it is, right? It's a very small interaction, at least in transition metals. So here, if you take a 3D element like iron or cobalt, you can see that the spin-orbit coupling energy per atom is one of the smallest contributions to the total energy. And yet, we know that it is very relevant for a number of effects, in particular in magnetism, right? So there are equilibrium effects that you see here listed on the left, like the magnetocrystalline anisotropy is due to spin-orbit coupling, antisymmetric exchange interaction or Jaluzinski-Marie interactions. And then there are non-equilibrium effects, starting from magnetic damping, but also transport effects like anisotropic magnetoresistance, anomalous Hall effect, spin Hall effect, etc. So, and in fact, if you take away spin-orbit coupling from a magnet, this magnet will not behave at all as a magnet anymore, right? For example, without magnetic anisotropy, we would not have a fixed magnetization. Without magnetic damping, we would not have a connection between spin and lattice, so it would be hard to excite and de-excite a magnet. And so this interaction between the spin system and the lattice and the orbital system is therefore very important. So today I'll focus on more on the transport effects, and in particular, those effects that allow for transforming a charge current into a spin current. Right? And so these effects can be then roughly subdivided into two categories. One is spin-dependent scattering, and where the trajectory of the electrons depends on the spins, and therefore you can have different trajectories for different spin orientations. And the other category is spin rotation, so where you can achieve a uniform spin polarization for electrons flowing in a given medium. For example, in a medium that lacks spatial inversion symmetry. And this is the case, for example, of the so-called Rush-Edelstein effect. So these effects are useful because they allow to obtain either a spin accumulation or a spin polarization, and then these non-equilibrium spin distributions can be used for controlling the orientation of the magnetization in magnets. So to give you a very brief and pictorial view of these two effects, I start with the Rush-Edelstein effect, where you have to imagine an interface. Okay, this can be, for example, a material with two dissimilar layers facing each other, where you have some charge transfer at the interface of these two materials. And this charge distributions then produce an electric field that is perpendicular to the interface itself. And then if you pass a current in the interface plane, this current, or the electrons in this current, will basically see this electric field as an effective magnetic field due to a Lorentz transformation in the rest frame of the electrons. And this effective magnetic fields will tend to orient the spin of the conduction electrons parallel to it, as you see in this cartoon. And this so-called Rashba magnetic field, right, is proportional to the current, and also to a material constant, which is here the Rashba constant, that basically tells us how strong this electric field is, and how strong spin-orbit coupling is in such a system. And then, due to this effective magnetic field, one can have a non-equilibrium spin polarization, okay, that is essentially proportional to the current itself. So that's one effect. And the other class of effects, this where we have spin-dependent scattering, is the family of spin-Hall effects. Now here you can have two types. So one is a extrinsic scattering effects due to impurities. And here, by analogy with Mott scattering, where you have scattering of electrons by local charges, one has spin-dependent trajectories of the electrons, right? This is due to the essentially how the electric field, the Coulomb field around the charge impurity is seen as a magnetic field by approaching electrons, and this will then deviate the electron's trajectory according to their spin. Okay. So these are extrinsic effects, but there are also intrinsic effects. Right? And intrinsic effects basically occur due to the band structure configuration, and they're also described in terms of an anomalous velocity or Berry curvature here. But the easiest way to understand them, in my opinion, at least from an intuitive point of view, is by imagining that electrons that travel in a metal, for example, in a transition metal, will hop between atomic sites. And in doing so, they sort of jump onto orbitals that are localized at atomic sites. And as they jump into an orbital that has a well-defined orbital momentum, then the probability of jumping into this orbital will depend on the spin of the electron because of spin-orbit coupling. And therefore, spins with opposite electrons with opposite spin orientation will acquire opposite quantities of angular momentum, and this results in an anomalous or transverse velocity. So then with this, as a result of this transverse velocity, electrons are deviated towards the edge of the sample and accumulate there. So what you have is actually a spin accumulation, so a disproportionation of the number of spins at one interface with respect to the opposite one, right, without necessarily having a charge imbalance. Okay. So now this edge spin accumulation that you see depicted here in this cross-sectional view of a conductor, right, occurs on a length scale that is determined by the spin diffusion length. Right, so essentially, the electrons deviated by the spin-Hall effect in this material will travel towards the interface, and they can only accumulate at the interface, and then they can backscatter, and the region over which this spin accumulation is observed is essentially determined by this parameter, which is the spin diffusion. Right. In a material like platinum, so in a heavy transition metal, this is of the order of a few nanometers. There are some discrepancies in the literature as to how much should this really be. And the other relevant parameter in such a process is the so-called spin-Hall angle, which is defined as the ratio of the spin-Hall conductivity to the longitudinal conductivity, or if you prefer, the ratio of the spin current to the charge current in units of number of electrons. And so this is an eight-dimensional parameter that essentially quantifies how strong is the charge to spin conversion effect. And this number in typical heavy metals, so 5D transition metals, is the order of 0.1. So about 10% of all the electrons flowing in a current in such a conductor are then transformed into spins, if you want, into net spin accumulation at the interface. There are also other interesting effects that occur when a charge flows in a material with strong spin-orbit coupling. For example, orbital Hall effects have been postulated by theory, not yet convincingly demonstrated by experiments. And also, spin currents can be generated at the interface between a magnetic and a non-magnetic material due to spin orbit dependent electron scattering or precession of electrons in a spin orbit, in an effective spin orbit field. Now, all these effects I will show you later. These are can be used for several purposes. I'd just like to show you how these can be measured, in particular in the metal. So the spin Hall effect has been first measured in 2004 by the group of Avshalom and the group of Jungwirth in semiconductor materials. And typically, magneto-optical techniques have been used to measure the spin accumulation in these materials. Right? You can do the same in a metal system, in principle, but only the magneto-optical signal that one expects from such a measurement is orders of magnitude smaller than in a semiconductor. So then this can still be done, as I said, and this is something that took several more years with respect to the first detection of the spin Hall effect in semiconductor. And you can see an example of such a measurement here. Here we have a platinum Hall bar. This is the structure defined by optical lithography. So this is platinum film that can be 5 to 50 or 100 nanometer thick. And then we send a current along the bar. And we place this device into a scanning optical microscope where we focus a laser beam on the surface of this bar, and we scan it across the bar itself. Right? So here you see an image of the profile of the sample. This is just the optical reflectivity in black here, and the noisy signal is the Kerr rotation that we measure in phase with an AC current that we send across the sample. Okay. So this Kerr signal is extremely small. It's the order of a few tens of nanorods for currents that are already the order of 10 to the 7 ampere per square centimeter. So it's quite a large current. And the signal also scales linearly with the current amplitude that we inject in the structure. So this is a good indication that this effect is really current dependent and, for example, not heat dependent. And another indication is that if we take a material with opposite spin orbit coupling with respect to platinum, like tungsten, we observe an opposite Kerr rotation. Then we can measure this effect as a function of thickness of the platinum layer. So here you have platinum thickness in the Kerr rotation. This is essentially a measure of the surface magnetization. And you see that the signal grows over a certain thickness, and that is a result of the fact that in order to observe accumulation, the thickness of the platinum Hall bar has to be larger than the spin diffusion length of the platinum itself. Okay. And the other important fact is that the sensitivity of MOC, of the magneto-optical Kerr effect, is several tens of nanometers. Okay. So we can then fit this curve and essentially convert it into a magnetization with the help of also ab initio electronic structure calculation that allow us to make this conversion between K-rotation and magnetization, and quantify this current-induced magnetization in platinum to the order of something like 10 to the minus 5 Bohr magnetons per atom, or if you want 100 spins per square micrometer. Now this is really small, right? But still corresponds to what is known for this material, so a spin-Hall angle of about 10%. Okay. And what I will show is that even if it's this spin accumulation is small in absolute quantity, the fact that spins are continuously flowing generates a substantial flow of angular momentum that then can be used for manipulating the magnetization in ferromagnets and ferrimagnets. So here now we know how to achieve charge spin conversion. And the question is what we can do with it, right? If we go from a current to the spin system. And the focus of this talk will be on sensing and switching the magnetization of magnetic systems. There are also interesting coupling effects that can be observed in such systems. I will just mention them briefly at the end. So the first family of effects concern transport, in particular magnetoresistance effects. And it is now known that there are many sort of exotic magnetoresistance effects that differ from the standard anisotropic magnetoresistance in ferromagnets or from the Lorentz magnetoresistance in non-magnetic conductors. And these are due essentially to this charge spin conversion that occurs in this family of systems, in particular this heavy metal ferromagnet or ferrimagnetic bilayers. Okay. And this includes spin-Hall magnetoresistance, Roche-by-Edelstein magnetoresistance, non-local spin-Hall magnetoresistance, Handley magnetoresistance, etc. But here I would like to focus on a different effect. And the way to introduce this is to make an analogy with the giant magnetoresistance, which I assume everybody knows what it is. So we have, in the standard GMR system, we have a magnetic trilayer where the two magnetic layers are separated by a non-magnetic space. And the basic principle here is that a current flowing in the system is spin polarized by one of the magnetic layers, let's say the bottom one. And when electrons then travel from the one layer to the other, then this spin polarized current will be either, let's say, blocked by the second ferromagnet that will act as a spin filter on the spin polarized current, depending on the sign of the spin polarization that is induced by the first ferromagnet, or will let most of the current pass if the two ferromagnets are aligned to each other. Okay. So in order to observe GMR, of course, you need at least two different magnetic layers to create the spin polarization. But if you have spin-orbit coupling in a non-magnetic system, then you can achieve spin polarization, a net spin polarization, just by one of the two effects or both that I've mentioned before. So you can pass a current into, for example, a cobalt platinum system and accumulate spins at the interface that have a well-defined direction due to either the spin-Hall effect or interfacial spin-dependent scattering effects. So in principle, one can observe a phenomenon that is similar to GMR, but with only one ferromagnetic layer. And this is, in fact, observed. Here you see the difference in resistance for the magnetization of the only ferromagnetic layers in the system pointing parallel or anti-parallel to the spin accumulation at the interface of the materials. And now, this also means that this system is quite peculiar because the resistance is not the same when you flow the current in, say, the positive or the negative direction. Okay. And so that's why we call it unidirectional spin-hole magnetoresistance, because it is a resistance that depends on either on the sign of the current or on the sign of the magnetization, which is different from typical magnetoresistances, which are a function of even powers of the magnetization. Right? So clearly, this is a nonlinear effect, okay, that therefore escapes also the reciprocity that one expects in electron transport. So this effect scales with the current. So we have a resistance that increases with the current. That's just because the spin accumulation is proportional to the current itself. And it has opposite sign for tantalum and platinum conductors, again, because the sign of the spin orbit coupling in these two materials is opposite. And it turns out that this effect is, or similar effects, so unidirectional magnetoresistance effect, are observed also in different classes of conductors, for example, magnetic semiconductors, topological insulators, and antiferromagnets. So they are quite common and essentially a signature of spin orbit coupling in this system. So we can also speculate or actually investigate the origin of the microscopic origin of this unidirectional magnetoresistance term. What we hypothesized in our first work was, in effect, very similar to GMR. So where essentially the electrons traveling in this bilayer system will be scattered more or less depending on the sign of the spin polarization at the interface with the ferromagnets. So this is called interface spin-dependent scattering. Then came Shulei's work. This is one of the first theory work on this effect, which showed that also you can have effects in the bulk of the ferromagnets due to essentially spin-dependent conductivity inside the ferromagnet. Okay, and this is also a phenomenon that is similar to GMR, where you have bulk spin-dependent scattering. And then there were many other works that have shown and also discussed the fact that when you inject a spin current into a magnet, the spin current can generate magnetic excitations, magnons, and then these magnons will scatter electrons, inducing an additional resistance term. Right? And the spin current can actually excite more magnons or damp the magnons. And so that's why one would observe either an increasing or decreasing resistance. So it turns out, these are our later experimental studies, that both of these effects, or actually the three types of effects, can exist at least in metallic ferromagnets. So these are measurements on platinum cobalt bilayers. And we see that there are different contributions to this unidirectional resistance here. One is really akin to GMR. This is what we call the spin-dependent scattering magnetoresistance. That depends only on the orientation of the magnetization and not on applied magnetic field. And another effect is visible at low magnetic field. This is due to the presence of magnons that are that are easier to excite when the system is not magnetically saturated. So all of these effects can actually be seen. So what can you do with such an effect? For example, you can use it to determine the absolute orientation of the magnetization of small magnets by performing just a two-terminal resistance measurement. And this will give you two levels of the resistance for magnetization pointing right or left. But you can also fabricate a system where you have two ferromagnets coupled to so sandwiching a non-magnetic conductor. And then in this case, you would observe the switching of the two magnetic layers independent of each other. So this effect, also similar to the other spin orbit induced magnetoresistance, can be used to detect, to sense the magnetization orientation of the system. Okay, so that's about sensing, but then very interestingly, one can also use the spin current to manipulate the magnetization of a magnetic layer, for example. So here it doesn't matter much which mechanism induces the spin accumulation. It can be the spin Hall effect, it can be an interfacial effect. But as long as you have a spin accumulation at the interface with a second material, which is magnetic, then this spin that accumulates at the interface will diffuse into the magnet and be absorbed in the magnet. And when a spin current is absorbed, this is equivalent to a torque, a magnetic torque. And there are actually two possible torques that can appear in such a case. One is called a damping-like torque because it acts in a way similar to magnetic damping. And the other one is called a field-like torque because it acts in a way similar to a static magnetic field. So this torque, which can also be characterized by the effective magnetic fields that corresponds to the torque, can be used to manipulate the magnetization in these systems. So in the literature, these torques have different names. People have been calling them in all different ways. So the field-like spin orbit torque has been called the Rashba torque, spin orbit field, spin orbit torque. Damping-like spin orbit torque has been called the spin Hall torque, spin transfer torque, Slonczewski torque, etc. Here I will call them field-like and damping-like spin orbit torques, where the spin orbit basically refers to the origin of the torques themselves. Okay. And typical values are the order of a few millitesla for these current densities, which are relatively large, but not as large as to damage the samples. So by injecting current pulses into a structure that contains a heavy metal, a ferromagnet, and a capping layer, if one pulses the current, then it is possible to reverse the orientation of the magnetization of this ferromagnet. And this can be done in a reversible way, so that if you use a positive pulse, you switch, say, up, and a negative pulse will switch down. And so what is actually occurring in such a system is that the current is transferring orbital to spin momentum to the magnetic system. And that allows for switching the magnetization of a ferromagnet without the need of a second ferromagnet to polarize a current. And all this is compatible with standard material systems that are already used in, for example, magnetic memories, etc. Okay, so this can be done. There are some subtleties as to the condition in which this can occur in perpendicularly magnetized layers, where there is a need of a symmetry breaking mechanism that can be, for example, an external magnetic field or some asymmetric structural feature of this magnetic dot, or in plane systems. Okay. Now, to show you how this works in a real dot, this is a picture of one of our samples. So this is an X-ray transmission image of essentially platinum strip line with a cobalt dot in the middle. And what you see, the large black areas here, these are the gold electrodes. So what we do is that we deposit this structure on a silicon nitride membrane, and we place it in a scanning transmission X-ray microscope, and we image the cobalt dot by tuning the X-ray energy to the cobalt absorption edge at the L3 edge. Okay. And then by changing the light polarization, we also achieve magnetic contrast by the X-ray magnetic circular dichroism effect. Okay. So you see here magnetization pointing up and down. And if we image this system as we pulse the current through the platinum strip, okay, here you see a negative current pulse followed by a positive current pulse. And we perform this in a pump probe manner. So we stroboscopically probe the transmitted X-ray intensity as we pulse the current. We observe that the magnetic contrast, the 6-MCD contrast, changes as soon as the current pulse is on. Okay, changes in one direction, and then when the opposite current pulses arrives, it switches back. And here, let me see if I can start this movie. This is a movie acquired by X-ray transmission microscopy. You see the reversal of the magnetization in the dot occurring by nucleation and propagation of a domain. Okay, I'll skip that. There are interesting things to say about how this reversal actually occurs by nucleating a domain always in the same position and propagating a domain well always in the same direction. But I'll skip that for reasons of time. And I will move to the application part, that is how to use this current-induced switching by spin-orbit torques in order to make devices. Okay. And of course, one of the most useful devices in spintronics is a magnetic tunnel junction, which I suppose you all know what it is. It's a device that is composed by two magnetic layers. One is a reference layer with a fixed magnetization. The other one is a free layer with a switchable magnetization separated by a tunnel barrier. And in the typical spin transfer torque magnetic tunnel junction, a current is passed through this magnetic stack. The current is spin polarized by the reference layer, and then the spin polarized current exerts a torque, spin torque on the free layer that can switch it back and forth. Now, this is using the spin transfer torque mechanism. But if we use the spin orbit torque mechanism, then the spin current is produced by current injection into a bottom heavy metal electrode here. This can switch the free layer without passing the current through the tunnel junction. And this avoids, for example, damage of the tunnel barrier while pulsing that can occur in STT. And it also avoids the possibility of inducing a write error while reading the state of the tunnel junction, which is performed by a tunneling magnetoresistance measurement through the top electrode. So now in this three-terminal devices, there are also other interesting effects besides spin orbit torque switching that can occur. One is that by having three terminals, one can still use current injection through the pillar, so spin transfer torque, to control the magnetization of the free layer. One can actually study the competition between these two torques on magnetization switching. And then there is a third effect that is called voltage control of magnetic anisotropy. That is basically the fact that when you apply a bias to a magnetic layer, you can actually modify the magnetocrystalline anisotropy of this layer by charge transfer effects. Okay. And this can, for example, assist the switching by reducing the magnetic anisotropy right at the time when this is useful, so when you want to switch the magnetization of the free layer. Okay. Now, if you compare the action of a spin transfer torque with that of a spin orbit torque, there is a notable difference. One is that the spin transfer torque, as it is produced by the current spin polarized by the reference layer, is actually collinear with the magnetization of the tunnel junction. And therefore, it can only act on the free layer when the free layer magnetization is not exactly parallel to the torque itself, right? So this means that there have to be some thermal fluctuations of the magnetization in order for this torque to become strong and start switching. And so that causes a delayed action or an incubation time. In principle, however, spin orbit torque is orthogonal to the magnetization of the free layer, and so it doesn't need to wait for fluctuations to misalign the free layer magnetization. So it has, in principle, immediate action. So that's one notable difference between the two torques, which is in principle useful for achieving fast switch. We'll see, however, that the situation is not as simple or ideal as it looks like. So here in this study, we have devices that were made at IMEC in Belgium in a collaboration with us, where essentially we obtained their devices for characterization and then fed back our results into the fabrication process. So devices look like this. We have these tunnel junctions. The ones we studied here are 80 nanometers in diameter. They're composed of a bottom tungsten layer. This is the heavy metal that brings the strong spin orbit coupling. A cold iron boron free layer with perpendicular magnetization, an MgO tunnel barrier, and a cold iron boron reference layer, and then a synthetic antiferromagnet structure. And as I said, we can pulse the junction using this three-terminal configuration, and so we can essentially use both spin orbit torque or spin transfer torque to switch. So here you see examples of real-time measurements. So we essentially we pulse the current into one of these two electrodes, and in real time we monitor the tunneling magnetoresistance of the junction. And that gives us an idea of what the magnetization is doing in the free layer. So if we first perform the experiments by using the top electrodes, so spin transfer torque only, and we perform a certain number of pulses, we see that we obtain different traces of the tunneling magnetoresistance. And these different traces are telling us that the magnetization is switching, so from the initial state to the final state. But that the switching process is certainly not reproducible, because as you see here, the point where the magnetization starts switching is essentially varying in a random way. And also the switching transition, so the ramp time during which the magnetization actually reverses, is variable, right? And so this is known for spin transfer torque. We were a bit more surprised to find not really similar, but also a stochastic behavior for spin orbit torque switching, because also here this initial time at which the magnetization starts changing appears to vary in a random way. Okay. And in fact, we can sort of reduce the randomness in the system by doing one of two things. One is to add, so combine the spin orbit torque pulse with the spin transfer torque pulse, which actually also means combining the VCMA, this voltage control of magnetic anisotropy, with spin orbit torque. In this, you can see that immediately it has a very strong effect in that the initial switching time, this T0, is reduced and becomes much more reproducible. And also this reversal time, the duration of the ramps becomes short. And if we then add a strong in-plane field that essentially helps the nucleation of a reverse domain in the system and the propagation of this domain, then this becomes a quasi-deterministic behavior where we have switching on a very short time scale. And this is also seen in this statistical distribution. So this is the initial switching time, T0. And you see for different values of the STT bias, right? And so we achieve a very strong reduction of this T0. And this is the ramp time, which is much shorter for SOT switching than for STT switching. And then the sum of the two gives us the total switching time. And this can be reduced also to below a nanosecond just by applying a larger in-plane field to assist the switching, or also by increasing the bias. Okay. So what is the reason of this finite delay time in spin-orbit torque switching that shouldn't be there because the torque is orthogonal to the magnetization? And the reason is that this systems that we study, this cold iron boron on tungsten, has a strong perpendicular anisotropy. And so the system is magnetically too rigid to be switched by the torque. And therefore, we need somehow to reduce the magnetic anisotropy before switching can occur. And this happens by Joule heating, essentially. So the current pulse not only applies a torque to the system, but also heats it. And by heating it, the magnetic anisotropy is reduced, also the saturation magnetization, but in particular, the magnetic anisotropy is reduced. And this makes it easier to switch in such a system. And so the stronger than the current pulse, the stronger torque, but also the stronger the heating in the system, and the faster the switching is. So there is this interesting interplay between all these different effects that are current-induced, but also heat-induced in such a three-terminal magnetic tunnel junction. Here I show a different type of device where we eliminate the need for an external in-plane field by essentially fabricating a magnetic layer on top of the junction itself, which produces a stray field on the free layer. And we achieve also here sub-nanosecond switching with more than 99.9% reliability in this type of devices. So then from the point of view of device application, it is interesting to compare the performances of a spin-orbit torque of a magnetic tunnel junction that is operated by spin-orbit torques versus spin transfer torques. And these are interesting comparisons if you want to make a magnetic random access memory, which nowadays are made using spin transfer torque magnetic tunnel junctions. So here, as you see in this table, if you talk about size, then spin transfer torque has a smaller size, smaller cell size than spin orbit torque tunnel junction because it's a two-terminal system rather than a three-terminal system. And with the materials in use today, the right energy of an SOT MRAM is still larger than STT. And that's because essentially the charge spin conversion in a material like tungsten is still a fraction of the total charge current. So in this case, spin transfer torque is more efficient. However, if we consider the right speed, then spin orbit torques are superior to spin transfer torque, as I've shown you. And in fact, in our tunnel junction, it's not even possible to switch the magnetization in a reliable way below 5 nanoseconds using spin transfer torques. This is due to phenomena like backhopping and other effects. So if you want to go really fast, then spin orbit torque works better. And by reducing the duration of a current pulse, then you also reduce the writing energy. Okay. And in terms of read speed and endurance, spin orbit torque is potentially more interesting than spin transfer torque because it eliminates write errors when reading the junction, and it doesn't pass a current through the tunnel pair. But of course, one of the areas of current research in this field is to increase the spin orbit torque efficiency, which basically means increasing the spin Hall angle in the material that is used to produce a spin current. So before concluding, I'd like to show you also that these type of effects are not limited to metallic systems. And in fact, much of the interest comes from the fact that there are sort of universal torques that can be used to control the magnetization in different classes of materials, including insulators. So here we have a magnetic garnet layer. This is a thulium iron garnet film with perpendicular magnetization. And this is a classical classroom experiments where you show the magnetic domains in a garnet layer. And here we see this is a magneto-optical Kerr effect image taken as we apply a magnetic field perpendicular to the plane of the film. And what you see is that these stripe domains form in the garnet, right? And here I forgot to say that these white regions here, these are, it's basically a platinum overlay in the shape of a hole bar that we patterned on top of a continuous garnet field. Okay. So when we apply an out-of-plane magnetic field, first the garnet that has no platinum on top changes the magnetization. Then we increase the strength of the field, and we see also the switching occurring in the platinum-covered regions, while the pure garnet magnetization saturates. So this is a classical field-induced switching of a garnet. Right? But it turns out that by pulsing the current in such a structure, we can control the magnetization in the garnet layer, but then just below the current line. This is seen here. So now we have a similar system, only the thulium iron garnet layer is 8 nanometer thick. And we pulse the current repeatedly and observe that the magnetization reverses starting from the center of the hole bar towards the two ends. Okay. And if we reverse the direction, if we start from this switch state and reverse the direction of the current, then essentially the magnetization switches back. Okay. And the interesting thing is that this only occurs underneath the platinum metal layer. So we can essentially write the magnetization where we want in this garnet by essentially patterning the platinum circuit on top of it. Okay. And we can not only write the magnetization, but also read it by exploiting one of these magnetoresistance effects induced by spin orbit coupling, in this case, the spin Hall magnetoresistance, which allows us to measure the switching of the magnetization. Here we have the switching induced by an out-of-plane field, and here the switching induced by a current. Okay, so I've come more or less to the end of the talk. I'll just show this last slide before concluding, just to mention that spin-orbit coupling is not only very useful to achieve charge-spin conversion, but also to engineer different and unusual types of couplings in magnetic films and small structures. And in particular, to achieve the so-called chiral coupling, which is essentially due to the Jaruzelski-Maury interaction, which is known for a very long time in bulk systems to induce non-collinear spin alignments. But in surface layers and in systems where you can actually pattern not only the shape of the magnetic elements, but also the magnetic anisotropy of these elements. For example, you can pattern a system such that you have a region with magnetization pointing up and a region with the magnetization pointing left. Okay, so one in plane, one out of plane. Then this Jaruzelski-Maury interaction induces a coupling between this orthogonal magnetization and essentially favors one orientation, say up left, versus another one, for example, up right. Okay. And this coupling effect can be used to essentially construct synthetic magnetic systems like synthetic antiferromagnets formed by chains of out-of-plane, in-plane, out-of-plane coupled magnets. One can pattern artificial spin ices or artificial spin lattices, even synthetic skyrmions with chiral magnetic configurations. And one can exploit these effects in combination with spin-orbit torques to create domain wall circuits and manipulate domain walls in a way that you can actually achieve the inversion of domain walls or construct majority spin gates that allow one to perform logic operation with domain walls. So with this, I conclude, and I just show this slide to stress once more that this charge spin conversion due to spin-orbit coupling and the spin-orbit torques can be used to induce several effects from switching to high-frequency oscillations, which I haven't mentioned in my talk, domain wall motion, and other effects. And that these effects are can be achieved in essentially all classes of magnetic materials, either directly or by proximity. And with that, I thank you for your attention.
Okay, thank you very much, Pietro. Let's thank the speaker for this nice talk. You can use the virtual or, you know, I just use.
Thank you.
So the seminar is now open to questions. Okay, I think I just asked the first question. Well, I have a couple of questions, you know. So first one is the spin Hall effect in semiconductors was observed like around 2004, and the effect in metals instead was observed much later, about decades later. So what is the difficulty?
Well, it's actually, so the first, I think one of the
direct observation, like using the magneto curl effect.
Yeah. So let me, okay. So here you have the measurements that you referred to, right? This is the first measurements by Kato et al. Of the current-induced spin accumulation in a gallium arsenide material, right? And here, this is made possible by Moog by the fact that even though the spinel angle is smaller in gallium arsenide compared to a heavy metal, the spin accumulation length is larger. Okay. So order of magnitude, so this is about 3 orders of magnitude larger. And that increases the amount of spin accumulation, but also allows you to probe it using the polar mode configuration, which is the most sensitive one. So you can actually see the spins accumulating at the edges of the conductor here. These are spins pointing up and down. Okay, whereas in our experiments, we detect spins in the center of the conductor, which are pointing right or left, and that has a lower sensitivity. So that's why in metals, this type of experiments is more difficult, but there were many indirect measurements of the spin-Hall effect, for example, in platinum by measuring the changes of damping, of magnetic damping induced by a current in a bilayer comprising a platinum in a magnetic layer, or so-called spin torque ferromagnetic resonance effect. So this have been measured around 2008 by the group of Ando in Japan and Dan Ralph and Bob Moorman in 2011 using spin torque FMR. And so to measure the effect of a spin current on the magnetization of a ferromagnet is a lot easier than detecting the spin accumulation in the magnetic conductor itself.
So the metallic system, in metallic system, so basically you will have a much shorter spin relaxation time. That's
yeah. So the spin relaxation time is the order of picosecond instead of nanosecond. The spin diffusion length is order of nanometer, and so this makes it more difficult to detect.
I see. Good. Thanks. Any other questions from the audience?
So can I have just a follow up on that last question? So I'm curious, as someone who does MOC measurements, and I was in the Oshlom group at the time when those measurements were being done. So to do MOC, to get the sensitivity to see that MOC signal on metal, was there any like particular tricks that you developed?
I mean, maybe not really, super smart tricks, but you have to be extremely careful. Here, I reported the number of measurements that were performed while we were doing ours. So it took us, 2 or 3 years to really come to some, from the setting up of the system and the measurements that we could trust. And basically, there was an early claim of these effects being observed in metals, which we believe is actually due to spurious effects. There were other null measurements. And let me see if I can show it here. Yeah, so one of the, the strongest effect you have to fight against is basically heat-induced changes of reflectivity, of the optical reflectivity of your sample that you see in this map of the reflectivity that occurs when you pulse the system. So this is Joule heating produced by the current, and you can see that it's stronger, for example, in the narrow section of the conductor is weaker where you have a broader section. And this can induce spurious effect even in a lock-in detection mode. So let's see if I have a picture of the setup. So here we have a system where, first of all, you have to use a microscope. So you have to probe locally. This is similar to the Santa Barbara experiment. And then we have to modulate the current. And we found out that the sinus modulation is much better than a square modulation that introduces more spurious effect, especially if the amplitude of the plus and minus pulses is not, balanced. And then we have a balance detector for the MOC signal, and we essentially detect first harmonic and second harmonic signal. First harmonic is proportional to the current. That's where we expect the magnetic signal. Second harmonic is proportional to heat-induced effects. And furthermore, to avoid additional spurious effects that can occur, then we physically switch the phase of the current by a relay. And then we average for, essentially just a single scan can take 48 hours on platinum. Right? And I don't know if we have, so we have also some control experiments where we measured the signal in aluminum, where we expected much smaller signal. And in fact, we do have a heat-induced change of optical reflectivity, but we don't have Kerr rotation. And we also changed the orientation of the optical of the laser beam. So invert the laser path, and that essentially switches the sign of the signal. And that's also a good sign in terms of MOC. So you have to be careful about all these effects, in particular because the current densities required are relatively high.
Mm-hmm. Mm-hmm.
So there are changes of temperature range from 1 Kelvin to 50 Kelvin, depending on the current density.
Thanks.
Oh.
Any other questions from the audience? Okay, I have another question on this unidirectional spin Hall magnetoresistance based on the magnon mechanism. Does this have a different length scale from the other two mechanisms?
You mean a different length scale?
Yeah, the magnetoresistance. The other two.
You mean like a thickness dependence?
Yeah, thickness dependence. Yes. Yeah, I know you showed it.
Yeah. I mean, yes. Although it's difficult to actually. Let me see if I can. It's difficult in practice to distinguish the different dependencies, but in the magnon. So it depends which thickness dependence you're talking about. So if you talk about the thickness dependence of the non-magnetic layer, then they should be very similar, because that that determines the amount of spin current that you inject in the ferromagnet, and that essentially depends on the thickness of the non-magnetic layer. So in that sense, no, it shouldn't depend. It shouldn't have a different dependence as the spin-dependent scattering effect. On the other hand, if you vary the thickness of the magnetic layer, then yes, it should have a different thickness dependence. Okay, and essentially because the magnon stiffness changes with the thickness of a magnetic layer. So we have some measurements of this, but I cannot.
Okay. But you did see the different landscape.
Yeah, you see effects of that there is a dependence on the thickness of the ferromagnet.
I see.
Yeah.
Good, thanks. So any other questions from the audience? Okay. Okay, if not, let's thank the speaker again. All right, if you want to stay a little longer to have an informal discussion unrecorded, you can do that. Let me stop recording.